Okay, your exam is on Friday, so some of the students asked me to go ahead and give you the answers to the bonding with the tutor and how to stick together in chemistry. And they wanted this to make sure that they were getting the right answers. I'm hoping that if you're watching this, you've already tried to do this on your own several times. Writing down the answers to this without going over it first and trying to figure it out is not going to help you at all. At all. So just don't do it. Try to do the problem set on your own. Try to actually read the slides and try to figure out what's going on. And then if you can't answer the questions, watch this video. Fast forward and look at the sections that you need help with. I would make sure I look at every problem, though, to make sure your thinking is all right. You have to ask yourself. Remember, we talked about quizzing yourself. You might think you know what you're doing, but you have to make sure you know what you're doing. That's why I explain every answer and why I want you to compare how you're thinking about it to what I'm saying. And if they match and you're getting the right answer, then everything's good. All right, let's go on. I'm not going to read the background information, although I thought the story was excellent, and this is the kind of thing that we see all the time in tutoring or as science teachers or even as tutoring in college. So there's this conversation, and there's these two guys. One's a tutor, it's a biology student, and he needs to review some chemistry. And the tutor said, sure. And he looked at this initial definition, and it says, electron shells are regions of three-dimensional space around a nucleus of an atom where electrons are found. Each electron shell can hold a certain number of electrons, and once it is full, any additional electrons will start to fill in the next shell. So when we're talking about three-dimensional space, I've said it already in the previous videos, you're talking about space, not specific roadways or what have you around the nucleus. And there's these areas, just a region. And if you watch the videos that I had already sent you, all four of them, I think they go through this very clearly. So if you're still confused, I would reference you to those videos and make sure you actually watch them and take notes. Again, copying someone's notes, which I've caught a few students copying notes, or just skimming through it and writing down what you think is important, which someone's also admitted to doing, is not going to help you. You have to understand what's going on. So three-dimensional space, and there's these layers within this three-dimensional space. And we've talked about the S&P orbitals, but none of that's really important when it comes to biology, and you'll see that we don't really talk about it in this project either. So moving forward, we're talking about space within which you will have some probability of finding these little electrons. Remember, electrons have -1 charges each, right? And electrons have a -1 charge. And they zoom around the atom in these spaces that we call shells. Okay, let's go on. So here's an electron. There's an electron shell. Remember, this is the Bohr atom, right? BOHR, Niels Bohr, and he came up with this idea. And he said, "This." I want to remind you again that this is a model. It's a model of an atom, and this model just simplifies something that's very complicated. Take something that's circling around in three-dimensional space at a quantum level, stuff that we can't really observe without changing, and we're just putting in this two-dimensional space, this little mini map, and we're saying that this is shell number 3, right? There's a shell number 2, and this is shell number 1. All right. Now in class we talked about the S&P orbital only to give you some background, but you need just to know that most of these shells fill up with 8 electrons. So most of the shells fill with 8 electrons. And that's why we say it's an octet. The biggest exception, of course, in biology and in science, there's usually an exception. Why is there an exception? Because this is a model. It's a simplified explanation. So there's a lot more going on than what we're talking about here. So let's not kid ourselves. This stuff is complicated, and we're trying to hit the highlights so that we can understand how biology, how biological systems make these really complicated molecules. So let's go ahead and talk about this Bohr atom, Bohr model. And you have 3 shells. The shell number 1, the first shell only holds 2. And it says so in the reading. I've said it in class. So for sure you should know that the first shell can only hold 2 electrons, while the rest of the shells, the second shell can hold 8 electrons, and the third shell can hold 18. Okay, so why is this third shell still only 8 around the outside? I'm really trying to avoid all this, but I guess I'm going to have to go ahead and explain this, at least this much. And I'm trying not to confuse you, and really I'm trying to cram all this chemistry into this short period of time so that you can understand what's going on with the building of biomolecules. It's unfortunate, but that's what we have to do. So now, when we look at this periodic table, the first shell is being filled in by this row. This is what we call period. This is called a period. So this first row only has 2. Notice it only has 2 atoms in it, hydrogen and helium. So it is only going to need 2 electrons to fill in. So hydrogen, I'm going to go ahead and do the math here. Hydrogen has 1 proton, right? A +1. So I'm going to go ahead and draw it +1, right? And so it's only going to need 1 electron. It's filling in the outer shell, the first shell, the first energy level. How do I know it's filling in the first energy level? Because it's in the first period of the periodic table. Has 1 proton, can hold 1 electron. Helium, on the other hand, when we take a look at it, has 2 protons. And I guess it has neutrons as well. And if you look at the mass of helium, let's take a closer look at helium. Helium has a mass of 4 and a proton number of 2. Remember, we're rounding off. So it has how many neutrons? Everybody should be saying 2 neutrons. 4 minus 2 is 2. 2 protons for sure, because that's the atomic number of helium, and the mass is equal to the protons plus the neutrons. And so therefore this number is the protons and the neutrons. This is the number of protons. So how do you find the neutrons? Subtract the atomic number from the mass number. So okay, so helium has a proton number of 2. I'm not going to worry about the mass right now, because all I really need to know is the charge. So I have +2 in the center. I have the first shell being filled, and so how many do I have? I happen to have 2. So is the outer shell filled? Yes. Why is the outer shell filled with only 2 and not 8? Because the first shell only holds 2. That's it. There's a lot of details that we can talk about in this, but we're not going to. All right, so that's it for the first energy level. That explains hydrogen. It explains why hydrogen and helium only have 2 in their valence shell, their outermost shell. So now let's take a look at the next row. The next row of the periodic table is row 2. And we're really only going to focus probably on the first 3 rows of the periodic table in biology. So you're dealing with these 2. This is row 2. Now, remember the column numbers. It's the column numbers that tells you how many valence shell electrons. Here, 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 and then finally here. Okay, so we're going to go ahead and discuss then these electrons. Let's do it. So for lithium, we know lithium is here in the first column, so it has 1 electron in its outer shell. But lithium is element number 3, so it has 3 protons. So let's go ahead and do the math. Plus, and plus, so 3 protons. In order to, the nucleus is going to pull in 3 electrons, 1 the first energy level for a shell, 2 it's full, so what is it going to do? It's going to pull another one in the third energy level. Let me draw this a little better. So in the first energy level it has 2, in the second energy level it has a third one. All right, so that's lithium. Now the next one is what? Beryllium, Be. So it's going to have 2, right, in the first energy level, and then the second energy level it's going to have how many? It has an atomic number of 4. How many, if it's going to be, and this is a key question, these we're talking about the neutral form, not the ions, but the neutral form of these. So if you have plus 4 in the center, let me go ahead and draw that because I didn't draw it. 1, 2, 3, 4. I have plus 4. I have to have how many electrons? I hope you said 4. So 1, 2, then 3, and 4. So you have 4 electrons, 2 in the first energy level. So 2 in the first energy level. This is the first energy level, and 2 in the second energy level. This is 2 in the first energy level and only 1 in the second energy level. So that's lithium. That's beryllium. Now let's go ahead and take a look at boron. Notice that there are no electrons in this particular spot, right? In the transition metals, there's no elements here, so there's nothing getting filled in. Boron is not here in this column; it's over here. There's a reason for it. We're not going to get into it, but just know that these are transition metals. These are non-metals. These are metals as well, but they're not transition metals. So let's take a look at boron, and let's say boron is in group what? In group 3, I hope you said. So we know it's going to have 3 electrons in the outer shell. Please notice something. Every time we increase a proton number, we're increasing the electrons. So every time we increase the proton number, we add another electron, right? Because we're sticking to this idea that these are neutral atoms. So as we go from 1 to 2 to 3 to, from 1 to 2, we fill in the first energy level. And when we go to 3, we have 1, 2, 3. We're filling in which level? The second energy level. And it happens to be the second period that we're doing that. So we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and finally neon. And so as we come across in this energy level, what we're seeing is that these electrons are filling in that particular energy level's electrons. All right, or space, the space available. All right, so let's go on and then start to do the next atom. The next atom is beryllium. Let's see, beryllium. Where am I? Beryllium has 1, 2, 3, 4. So that's 4. 1, 2, 3, 4. 4 protons, 4 electrons. We're good. Now, the next element is boron. So I wonder if I could erase. Let's see. Oh, that's not erase. All right. So now we're going to go ahead and do boron. Oops. We're going to go ahead and do boron, carbon, nitrogen, oxygen, fluorine. So boron, carbon, nitrogen, oxygen, fluorine, and neon. So in boron, again, already the first in all of them, right? We already filled in. Boron has 5 protons. I'm just going to put the number 5. So we have 2 in the S, and all of these are going to have 2 in the S, right? So what I did is I actually drew one too many shells I drew 3 shells, but I know that for boron and for everything in the second row, I only need 2 shells. You should know that, right? So I'm not gonna. You can ignore that blue line. We can use it later, but for now, ignore the blue line. That's not the valence shell. The valence shell is going to be the second one. So this is valence shell 1. This is valence shell 2. I'm sorry. This is energy level 1. This is energy level 2. The third shell you can ignore. The third shell is for when we fill in the third energy level. All right, so boron has 5 electrons, so we can fill them in. 1, 2, 3, 4, and 5. That's fine. That's boron. It has 5 electrons, 2 in the first, and 3 in the second. Now we go on to carbon. It has 1, 2. Carbon has 6 electrons total. 3, 4, 5, 6. This has 3 energy levels in the outer shell, right? 3 valence electrons. This has 4 valence electrons. And of course it matches up. It matches up here with the columns. Nitrogen has 7, right? 7 total electrons. 1, 2, 3, 4, 5, 6, and 7. So it has, in the outer shell, it has 5, all right? I'm pointing to the outer shell. This is oxygen. This is an O. So let me go ahead and draw this as an O. This is an O, not another shell. So it's hard to say. It's hard to see that. But in oxygen, we have then 8, right? So 1, 2, 3, 4, 5, 6, 7, and 8 electrons in the outer shell. Again, ignoring that blue line. So here you have 8 in the valence shell. Fluorine has 9 electrons total. So 1, 2 in the first shell, 3, 4, 5, 6, 7, 8, 9. So there's 9 electrons in the outer shell. And then neon has 10 total. So 1, 2, 3, 4, 5. Ooh, I'm just going crazy here. I don't know why I just did that. I was testing you. No, I wasn't. I just made a mistake. So 1s is 2 electrons, and then 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons in the second shell. In the second shell, how many... look at what I did. I made all kinds of mistakes. This is not 8 in the outer shell. This is not 9 in the outer shell. 8 and 9 total, but this has 6 in the outer shell. This has 7 in the outer shell. And this has 8 in the outer shell. All right. So in any case, what you see is in the valence shells, V for valence, the column that has a full octet is this row 8. Or column 8, excuse me, column 8, and you can see it right here that this column right here running down the side is column 8. All right, so every one of these noble gases, every one of them has 8 in the outer shell. So all of these have 8 in the outer shell. So all of them are full. They don't really want to react. So that's really going to be key. Now let's go ahead and do the last row that we're going to do, which is the third row. So we did row 1, row 2. Now we're going to do row 3. So here's sodium, and we're going to go ahead and put 11. So we got 1, 2. There's a 2 in the inner shell. 3, 4, 5, 6, 7, 8, 9, 10. So it has 10. All right, so the inner shell is done. It's filled in. I only have 1 in the outer shell. I'm going to quickly point something out that'll help you much later on. If I did neon again, if I did neon up here, and I did 2 electrons in the outer shell here, right? So the neon has a 10, right? And then the second shell, and 1, 2, 3, 4, 5, 6. So that's 2, 3, 4, 5, 6, 7, 8, 9, and 10, because neon has 10 electrons in total. Do you see that neon's where the electrons in? If I got rid of the center so that you couldn't tell if you didn't know that this was neon, if you just had some kind of like blob here, something was obstructing that, and you looked at this pattern of 10 electrons, 2 in the inner shell and 8 around the outside, isn't that pattern the same as these in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Aren't these 10 here, these 10 in here, the same as neon? Their electron configuration, aren't they? Doesn't this inner part of sodium have the electron configuration of this noble gas? Well, it turns out all of these do. Every one of these elements, all these atoms in this column, the inner shells all resemble, and this goes for these first two, that of a noble gas, which is another way of looking at why when they get rid of this outer electron, they have the electron configuration of noble gas, and why they don't react very well. Because noble gases, these elements here, they're gases at room temperature. They don't react with it much. They are considered inert chemically, and so if we can that's why these atoms, these elements all want to get to 8 around in the outer electron, because at some point, in some point, once they reach that 8 electrons in the outer shell, in the valence shell, that atom becomes stable. It becomes energetically stable. All right. So if this sodium can get rid of this 1 electron, it can have the electron configuration of the noble gas that came before it. So lithium, you get rid of lithium's outer shell, and go ahead and take a look at it. If you have lithium here, and lithium is +3, and it has has 2. And then has a second shell, because it's in the second row, has 1 electron, right? Doesn't that inner shell look a lot like helium? Helium has but 2 electrons, and it has 2 electrons in a shell. We call that stable, and it is a full octet. So there's this 2. Doesn't this look a lot like this, right? Except, of course, you have +3. So this electron configuration, where the electrons are, where they're filled in, looks a lot like the noble gas that came before it. Lithium looks a lot like helium. So that's a pattern you might want to look at and think about. All right, so let's take a look at magnesium. You see 1 here, and it fills in. We know that the second shell is filled in too. How do I know the second shell is filled in? Because I'm in the third shell already. So I can put 8, 1, 2, 3, 4, 5, 6, 7, and 8. I can put 8 around in this second shell, and be confident that that's filled in. That's 8. In 9 and 10, how many do I need in the outer shell? 2 more, 1 and 2. Now here I had 1 in the outer shell right here, and I added 1 proton, so I should add another 1 more electron, so that's 2 in the outer shell. So far it's all making sense to me. I go on to 13. There's 13 of them. So again, the first 2 shells are filled in for sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's 10 electrons in the inner shells. So here I had 2, right? 2 electrons in the outer shell. I added 1 more electron, 1 more proton. So I have to have, how many do you think I need to have? Hopefully you said 3. And this continues until what? What do you think is going to make the difference? 1, 2, 3, and then of course I'll have 4, right? Each time I'm adding 1 proton, so I'm adding 1 electron. So go ahead and add fill in the inner ones, because there should be 8 here, and then 2 here, so that's 10 total, plus the other 4 there on the outermost shell, the valence shell. That gives you 14, and silicon is 14, right? And that's in the 4th row, so that's all making sense, right? It's in the 4th row. It has 4 electrons in the outer shell. 1, 2, 3, and 4. It has 14 pluses, so it's 14 total electrons. And then we keep filling them in. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So that's 5 in the outer shell. And we do the same for sulfur. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So that's 6 in the outer shell. And again, each one on the inside has 10, doesn't it? The inside, the only thing that's different among these as far as electron configuration, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. 1, 2, 3, 4, 3, 4, 5, 6. I got 9. I'm not sure where I messed up there. So let's count these. I messed up somewhere. So 1, 2, then 3, 4, 5, 6, 7, 8, 9, 10. That's all right. Then 1, 2, 3, 4, 5, 6, 7. There should be 17. This is an extra one. So let me erase. So this is an extra one, so let's get rid of that. So when let's count again. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 17 total. 7 in the outer shell. I put an extra 1, extra 2. All right. And of course, with argon, you have all 18 filled in. 4, 5, 3, 4, 5, 6, 7, 8. 8 and 2. That's 8. Plus the 2 inside is 10, 11, 12, 13, 14, 15, 16, 17, and 18. So I have 18 there in the outer shell. I just want to point this out again. Everything on the inside of these, all of these, on the inside of this outer shell, this is the 3rd shell. This is the only thing that's different. The 3rd shell is the only thing that's different in the pattern of yellow electrons, right? So you have 8, you have 10 inside here, 10 in 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 here, and 10 in here. The only difference is the valence shells. This valence here has 1 valence electron. This one has 2 valence electrons. This one has 3 valence electrons. This one has 4 valence electrons. This one 5 valence electrons. This one's 6 valence electrons. This one's 7 valence electrons. And this one's 8 valence electrons. So again, because this element here is in group 8, has a full octet, it's a noble gas, is inert, does not want to chemically react. This one just needs 1 more to have a pattern like the noble gas, so it can be neutral. And have a full octet. Well, it won't be neutral, but it'll have a full octet. And so each of these have a full octet. It doesn't matter to them if they lose an electron and become like the element before it, like happens with sodium, where it loses its electron and becomes like neon, right? or whether it gains an electron and becomes like the element that comes after it. In this case, chlorine would gain an electron and become like argon, so it'd have its full outer shell. So that's, if you look at it and think about it, that takes care of your first 3 rows. Also, it shows that there's a mistake by the publishers of this little this activity, which is small. I mean, well, I don't want to call it minor, but it's a mistake, and I'll clarify when we get to the question. So let's go on. So here we have this again is more of that conversation, and it talks about how the next shell can hold 8 electrons, and any additional electrons will have to go on to the 3rd shell, and so on. We just saw that. I just did it for you. I stepped you through it. I showed you what the electron orbitals look like, what the Lewis dot structure of each of those atoms looks like for the first 3 rows. You can go back and rewind it if you want. Okay, so we're going on, and it goes on to talk about some other things. And here it says, well, they continued, and it says also, if the valence shell of an atom can hold a maximum of 8 electrons but only contains 5 or 6, the atom will try to gain electrons by sharing or taking them from another atom to complete the valence shell. Also, if the same valence shell only contains 1 or 2, and we've discussed this before, the atom will likely donate those electrons. So the first 2 columns, again, I'll ask this question of the columns here. Which 2 columns have only 1 or 2 electrons in a valence shell? That's these. This is why when you look at the ionic bonding video that says 15 minutes long, you see that this column will lose 1 electron and become positive charge with a positive 1 charge, so that it can have a full octet. This column will have a +2 charge because it'll get rid of that electron and have a full octet. Now, on the other side of the periodic table, these 2 columns each need 1 or 2, and specifically this one only needs 1 electron to become a noble gas. So whenever you see this column mixing with either one of these 2, what you're going to get, you could almost bet that what you're going to end up with is a salt. So you have lithium fluoride as a salt, beryllium fluoride as a salt, sodium fluoride is a salt, sodium chloride, table salt, right, is a salt, calcium chloride, which is rock salt. All these are different kinds of salts, and all a salt is 2 atoms ionically bonded with one another. So these 2 columns with this column form all these different kinds of salts. All right, so that takes us through that kind of bonding. Let's go on and try to answer the questions. So now let's go ahead and give it a shot. Let's take a look at this question here. We covered this in class, and the mistake lies here, I believe. This is not the Lewis dot structure of argon, right? Argon has 18. Argon is in the 3rd row. It's the last element of the 3rd row. So what this is the electron configuration of neon, right? I pointed that out to a couple kids in class, and unfortunately I didn't notice it until I had already copied it. So, and in fact, not till today. So we'd have to, in order to make electron configuration, you can go back and rewind and see it. But in order to make this electron configuration accurate, we'd have to add then, hold on a second, let me change colors. We'd have to add another 8 electrons. 1, 2, 3, 4, 5, 6, 7, and 8. If you look at argon on the periodic table, what you're going to find is that argon has a +18 charge. So argon has a +18 charge. You need 18 electrons. And if you don't have 18 electrons, then it's not argon. Right? And 18 protons, you don't have argon. If you have 18 protons, then it's neutral, as it says here that it's neutral, right? It says it right here, it's neutral. If it's going to be neutral, it has 18 protons, it has to have 18 electrons. So this is kind of a mistake on the problem set. So B is the answer, but the electron configuration was wrong. So which atom would be chemically inert? It would be argon, because it's a full octet, but there should be a 3rd shell. All right, so that was a mistake that needed to be clarified. This is fluorine. It needs an electron, so it's going to chemically react. In fact, it's definitely reactive. Lithium is very reactive. It will explode in water. It needs to get rid of this electron. It gets rid of it at any cost. No problem to it. And then, of course, once it gets rid of it, it looks like helium as far as its electron orbital, right? Its shell. That shell is full just like helium. Here's oxygen. There's 1, 2, 3, 4, 5, 6, 7, 8. Look in the periodic table. You will see that oxygen is indeed a +8, right? And you can look and see lithium is indeed a +3. And fluorine is 1, 2, 3, 4, 5, 6, 7, 8, 9 is a +9. And go ahead and take a look at them. And you'll notice that where I could tell you right now, just by the electron configuration, that fluorine is in the second row. How do I know it's in the second row? Because it's filling in which shell? The second shell. The shell number tells you what row they're in. Lithium is filling in its second shell, so it's also in the second row. Argon, if you look at it, is in the third row, which tells you that there was something wrong with this electron configuration. So then here, oxygen, you'll find it in the second row because it's filling in that second shell. All right, so let's go ahead and move forward. So that's the answer to that question. That's why the answer is the way it is. Hopefully you've been watching the video, or if you already understood it, you got it straight in. All right, so then it goes on and talks some more about what an ionic bond is. And it says an ionic bond is a chemical bond that involves the transfer of electrons. So you're switching electrons, like we said about sodium and chloride. Any of the elements in the first two columns combined with any of the elements in that seventh column, right? It involves a transfer of electrons from one atom to another so that both atoms will be left with a full valence shell. Okay, so let's move on. And it talks additionally, ionic bonds are typically formed between metals and nonmetals, and we looked at what those are. An example is an ionic bond between a sodium atom and a chlorine atom, which we've already talked about numerous times. A sodium atom and has 1 electron in a valence shell. A chlorine has 7. Group 1, group 7. The sodium atom will donate its 1 valence electron to chlorine atom, and both of them will have valence shells, full outer shells, full valence shells. So here's the example. It's really clear. This is sodium. I already drew it for you. You know this is a +11. Count the electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're good. And here's chlorine with its number of electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And it is atomic number 17. It is in the 7th row. When these two come together, far right, far left, they come together, this electron in the outer shell will just be pulled in and fill in the outer shell for chlorine. When it does that, this shell disappears, and what's inside? The noble gas configuration of neon. Because again, as I showed you earlier, this is now a full octet. And which energy levels has a full octet? The second energy level has a full octet. And what element in the noble gases has a second energy level that has a full octet? That's neon. Neon has that second energy level full. So all of these, this also looks like neon if you got rid of this outer shell. But it's not going to chlorine doesn't want to look like neon. It wants to look like argon. So it wants to fill in that third energy level, 1, 2, 3. And as you see, it takes it, it fills it in. There's a problem. What's the problem? Remember our 2 rules. Atoms and molecules, these little things want to be neutral, and atoms want a full octet. Well, this is no longer neutral. It has an electron sitting here. And this one's missing this one's missing an electron. This has an extra electron. This has a -1, and this has a +1. How do I know what charge an atom has? It's one of the questions people ask today. Well, chlorine, as we said, had 17 protons. Let's look at chlorine. It has 17 protons. That's 17 plus charges, right? And then you added an extra electron. So instead of 17, you had 18 electrons. All right, so add those together. 17 pluses minus 18 is -1. That should Hopefully that gets you that's in your head. So when you have sodium, Na has now 11 protons, right? 11 protons. And so naturally it has 11, when it's neutral, it has 11 electrons. But it lost one, didn't it? So now it only has 10 electrons. Why does it have 10 electrons? Because it got taken, right? Chlorine took it. That's how come it has an extra one. It had only 17 when it was neutral, but now it took that extra electron, and now you have 18 minuses plus 17 pluses. 17 minus 18 is -1. Well, what's going to happen then with 11 positives minus 10 negatives equals what? A +1. And that's why you have this +1 here. So how do we balance out the charges? How do these two things balance out charges if they're going to have a +1 and a -1? Do they just keep their charges? Absolutely not. They don't keep their charges. They stick near each other. The plus and the minus stick near each other. The plus and the minus stick near each other like little magnets they pull. So the plus and the minus stick near each other, which means but what's +1 minus 1 equals 0. So they have a net, we call that net, 0 charge, right? Okay, moving on. All right, so here we have another question. What is likely to happen to the electrons when a potassium atom bonds with a chlorine atom? You should be able to quickly run through this with a periodic table at hand. So if we take a look at our periodic table here, all right, potassium is a +19, chlorine is a +17. Now, yes, I could go through all the trouble that I just went through, right, and draw out the Lewis dot structures with all the inner electrons and outer electrons. But which one am I really interested in? I'm only interested in the valence electrons. For what? Two atoms, protein for potassium and chlorine. So look at potassium, and what row is it in? It's in row 1. Where's chlorine? In row 7. So I can do a little cheat, can't I? I could do a Lewis dot structure. I don't have to do the Bohr atom. I could just do the Lewis dot structure. Lewis dots are much easier because then all I have to worry about is the outer shell. So I know potassium is row 1, so I know potassium has a plus I'm sorry, it's not plus. Potassium has this single electron in its outer shell, and I know chlorine is going to be added to it, and I know chlorine is going to have 1, 2, 3, 4, 5, 6, and 7. Why does chlorine have? How do I know chlorine has 7? It's in the 7th column. Why? And again, 7th column, but I'm not counting these middle sections, these transition metals. It's 1, 2, 3, 4, 5, 6, 7. And of course, the noble gases are full. They're at number 8, but they're full and they're not going to react. So these two are coming together. All right. I know that everything inside here, everything inside there is what? Hopefully by now you understand that everything in here is full, right? So if I take this away, the outer shell will be 8. Remember that. Okay. So let's say we have the chemical reaction occur. It happens. All right. I'm going to draw this arrow vertically just because of the space that I have. So we have an arrow. There's a chemical reaction occurs. And something happens. That something is that potassium loses this electron. This electron is lost to potassium, right? And where's that electron going to end up going? It's going to go over to chlorine because chlorine is going to take it. Potassium is more than willing to give it. It means it's going to have a full outer shell, so it's happy. So what happens is potassium now has a full outer shell. 1, 2, 3, 4, 5, 6, 7, 8. The full outer shell. That's all I'm worried about with Lewis dot structures, the outer shell. But of course it has a what? A +1 charge. Why did it get a +1 charge? Because it lost this electron. This electron was lost. And where did it go? It went here. It got taken by chlorine. All right. So this electron left and went to chlorine. So this electron left and went to chlorine. When that occurred, chlorine then became what? became an element with an atom with a full octet. All 8 are there. But the full octet for chlorine means it has a negative 1. Why? We just did the math a minute ago. The chlorine has a negative 1 because there's an extra electron. Instead of 17 electrons, it has 18, and potassium, instead of having 19 electrons, has 18. So actually, they both have 18 electrons. So they both have the same shells filled in. So that would suggest that potassium was 1 energy level ahead. And let's go ahead and take a look at it. Chlorine is here in this row, which is row 3, and potassium is in row 4. So that makes absolute sense. You got rid of this electron here that was in row 4. So these, so in the outer shell, which is row 4, 4th energy level, that meant that this is what? The 3rd energy level. It is filled. This one took the electron into what energy level? The 3rd energy level. So now their electron configurations look alike. This has a +1. This has a -1. They stick near each other so that they can neutralize each other, because all atoms want to be neutral, right? So let's go ahead and try to answer this then as best we can. Jeez. Sorry about that. I'm trying to get that periodic table. I'm just going to be lost to us, I think, until I can get it all to the side there. All right, so the question that's being asked of us then is, what is likely to happen when these electrons when the potassium atom bonds with the chlorine atom? What happened? Potassium gave it, chlorine took it, they formed a salt, they have ions, they formed ions. This is called an ionic bond. That's what happened. Let's see if that's the answer choice. I don't know, I haven't looked at the answers. So chlorine loses an electron and potassium gains an electron. Is that what happened? Chlorine lost an electron and potassium gained one? No. The opposite happened. So we know that that is not an answer. That's an easy thinking question. Let's just checking to see if you understand which one's gaining and losing. Potassium and chlorine share electrons. Are they sharing? They are not sharing. That would be covalent. This is ionic. Potassium loses an electron and chlorine gains an electron. Well, that's exactly what happened. So that's correct. This is the answer. And none of the above is not an answer. All right? So that's it. That's how you answer these questions. You have to know. Of course, all you really had to know, if you didn't have to draw out these electrons, I wanted to show it to you, but you didn't have to draw them out. All you really have to know is that, hold on a sec, that potassium is in the far left, right? And chlorine's in the far right. You know that that means it's going to be an ionic bond. One's going to take, you should know the metal's going to give it and become positive, and the chlorine and the what we call halogens, that's the atoms, the elements in the 7th column, are going to grab it. So here's, so it says, good, now let me give you some examples of why ionic bonds are relevant to our lives. Ionic bonds form salts. We talked about that already. And other compounds that are very important in the human body. When ionic bonds in the salt sodium chloride are broken and form sodium ions and chloride ions, the sodium ions are used to help regulate blood volume, blood pressure, and chloride ions can be used to help balance pH in the body and transmit nerve impulses. So all that's true, and we'll talk more about that later in the year. Let's move on. And so it says ionic bonds also help form and maintain three-dimensional shapes of proteins, which can affect the way proteins such as enzymes and antibodies function. We haven't learned about enzymes or antibodies yet, but those are proteins in your body that help regulate chemical reactions. And so we will learn about these in 2 weeks. In fact, several human diseases are actually caused by misfolded proteins. So proteins that are misfolded because of these ionic bonds go bad. They include things like Alzheimer's. You've heard of Alzheimer's before. I don't think you've heard of Creutzfeldt-Jakob disease, but that's also one of them. There's others as well. There's insomnia. And it's a fatal form of insomnia. Insomnia means you can't sleep, Okay, so it's interesting that these are all caused by these ionic bonds that we're talking about. So let's go on to the next question. Now let me explain the covalent bonds. Now we're going to talk about sharing, and then there's something called polar and nonpolar bonds, and we'll talk about what that means. All right, so the next question is, what does electronegativity mean? And we discussed it in that video that I sent you earlier, but electronegativity is really how strongly the atom pulls on the electron. So let's take a look. Electronegativity is the capacity of an atom to attract electrons to itself, right? How strongly the atom attracts electrons. The atom with high electronegativity has a stronger electron attraction. An atom with low electronegativity has a low attraction for electrons. All right, so let's go on and move on. For example, two hydrogen atoms bond together. They form electrons that are equally because they share equally because of the same electronegativity, the same element. That's the key. This is the key. That if you have two elements that are the same and they're bonded together, notice how one hydrogen had one electron, the other had one. Together they share the two. They're going to share evenly. And the reason they share evenly is they have the same electronegativity. Why do they have the same electronegativity? Because of the same element. Let's move on. All right, which of these molecules contains a nonpolar covalent bond? So here again, very simple. Is it going to be sodium chloride? Sodium is in the far left, chloride the far right. I know that's an ionic bond, so this is ionic. And since I just went through drawing all that and explaining it, I'm not going to go ahead and do that again. I think you got it. So this is ionic. So I hope you know that by now. And CO2. Well, CO2 is, in fact, a covalent bond. You have a carbon, and it's bonded to an oxygen. And this carbon is bonded to two oxygens. How many bonds does oxygen make? Well, oxygen needs two electrons. I'm going to skip the electron orbitals. I'll draw it later for you if you like. I drew it in one of these in class, but this is what it ends up being. You know what? I guess I'm not going to skip it because I think it's important enough that if you want to, you can skip through this. If you want to see it, keep looking, and let's figure this out. So oxygen has 6 electrons in its outer shell, right? 1, 2, 3, 4, 5, 6. It needs 2. Carbon has 4 in its outer shell. 1, 2, 3, 4. It needs 4. I think you should know that by now. That part you should know, right? This idea that these atoms have their valence shell, carbon having 4 and oxygen 6, and the fact that they need 8. Everybody should know that. I've gone over it millions of times. So this is 4 electrons. It wants 8, so it needs to somehow get 4 more. This has 6. It wants 8, so it somehow has to get 2 more. Well, remember, in this case, and as in most cases in sharing means that everybody in the sharing pair owns those electrons. So if we take a look at these two are sharing. So this atom, oxygen, has those 2, and carbon has those 2. So let's take a moment and count how many we have here. Oxygen has 1, 2, 3, 4, 5, 6, 7. Why 7? Because they're sharing these 2. Carbon has 1, 2, 3, 4, 5. Why 5? Because it's sharing these 2. Now, it could also share these 2, right? This same pair of atoms can share these 2. All right. So now, how many electrons does oxygen have now? 1, 2, 3, 4, 5, 6, 7, 8. Why is there 8? Because these 2 belong to this oxygen. These 2 belong to this oxygen. How many does this carbon have? 1, 2, 3, 4, 5, 6. Has 6. But wait a minute, Mr. Mendoza. You said that these 2 belong to the oxygen and that these 2 belong to the oxygen. That's right, they do. But they also belong to the carbon. That's what sharing means. They belong to both partners. Now we go ahead and take a look at this, the other side. If this carbon needs 2 more, and here this oxygen still needs 2, gee, they could share these 2 and these 2, right? So we go ahead and draw it out, and you see that there's a sharing that happens here, and there's a sharing that happens here. These are all bonds. These are all chemical bonds. These chemical bonds, these sharing, they're called covalent. So that carbon is double bonded to an oxygen, which is double bonded again to this oxygen. I'm not going to draw the electrons, the outer shell electrons normally, but I'll go ahead and draw them here. So if you remember, each of these is 2 electrons, right? If you put a line between these two, that's what they're forming. That's what this line is. And that's why there's 2 here, because there's 2 bonds. So there's 2 bonds. So that's 2 and 4. How many more does it have? It has these 4 as well, doesn't it? That's why it has a full octet. So it's 1, 2, 3, 4, 5, 6, 7, 8. This has 8. Check. So over here is 1, 2, 3, 4, 5, 6, 7, 8. This has 8. Check. What about carbon? Does it have 8? I don't see any dots. 2, 4, 6, 8. Carbon is full as well. So everybody in this carbon dioxide molecule has 8 electrons. This is settled. This is sharing. This is sharing. Notice that carbon and oxygen are near each other. Not like these two. These two are far away from each other. Far left, far right. These two are right near each other. They're both nonmetals. This is a metal. This is a nonmetal. Nonmetals tend to form negative ions. Sodium metals tend to form positive ions. That's pretty much it. All right, so that takes care of that. Let's take a look at the next one. That's CO2. So this is ionic. We know that. This is this polar? Is this polar or nonpolar? This tends to be. Actually turns out to be. The bond itself is polar, but the molecule, the whole molecule, tends to be nonpolar because this one tends to pull the electrons a little more, right? This is oxygen, so it tends to pull a little more. This oxygen tends to pull a little more. But since they pull in opposite directions, they end up equalizing out. You don't need to know any of that. I just want to let you know why this is the whole molecule is nonpolar. So this doesn't really have a nonpolar bond. So this one's out. All right. And we take a look at magnesium and oxygen. What do we form there? All right, so when we have, you'll see magnesium is a metal, oxygen a nonmetal, very much like sodium and chloride. If you take a look at the periodic table, oxygen again. Let me go ahead and get rid of this other older material. So this one again, this one here is ionic. It's not, there's no really nonpolar covalent bonds here. If we take a look at magnesium oxide is ionic as well. How do I know it's ionic? I'm not going to go through the electrons being switched for you, but you know that magnesium is a metal. This is a nonmetal. This is far left. This is far right. They're going to form an ionic bond. It turns out magnesium ends up having a +2 charge, and oxygen ends up having a -2 charge. You should be able to do that. Why don't you go ahead and do that and see if you understand it. And that is called magnesium oxide. +2 -2 is a net 0 charge, which is why it's electrically neutral. So this is ionic. That's no good. All right. So then finally we end up with this molecule at the bottom, this 2 carbons. How do I know that 2 carbons are bonded with each other? Hydrogen can only make 1 bond. So you can go ahead and try to manipulate it any way you want. What you're going to find is the only possible answer you're going to get is that the 2 carbons are bonded to each other, and then the 2 carbons are also bonded to the 2 hydrogens. It's really the only way it works out. You have to remember, you have to work it out so that everybody has a full outer shell. So when we go ahead and do the bonding, you'll see these 2 are going to share, which gives this hydrogen 2 electrons in the outer shell. It's happy. These 2 are going to share, which gives this hydrogen 2 electrons in the outer shell. It's happy. This atom here has 1, 2, 3, 4, 5. This atom here has 1, 2, 3, 4, 5. And remember, they want 8, so how can we do it? And you could sit there and work it out if you like, or you can go ahead and take my word for it. What's going to happen is you're going to take and make a pair here. So that's going to be 1 pair. So that's, now let's do the math. 2, 4, 5, 6. Still needs 2 more electrons. What can it do? What can these carbons possibly do? They can go ahead and share again. All right, and then they can share again. So the three different pairings. And so when we draw it out, it turns out that you have carbon triple bonded to carbon, right? Singly bonded to hydrogen, singly bonded to hydrogen. And that gives you how many electrons in each of these atoms. Let's count them. 2, 4, 6, 8. So this atom is happy. Check. Same thing here. 8. This atom has 2. This atom has 2. This is, everybody has a full octet. Everybody's neutral. Everybody's sharing. Everybody's happy. These two are exactly the same atoms, so they're definitely a nonpolar covalent bond. This is where you get a nonpolar covalent bond. These two are sharing. These two are sharing. But the key is that as soon as you see this, for sure you know it's nonpolar covalent. So that's going to be your answer. So D is your answer. That's your example of a nonpolar covalent bond. Let's go ahead and go to the next problem. So here you talk about polar covalent bonds, a chemical bond that occurs when electrons are not shared equally. The classic example is water. That's one of water's special properties. And the higher the electronegativity gain, the stronger the potential negative charge. So let's go ahead and take a look. This unequal sharing. Polar covalent bonds result in charge separations. For example, hydrogen chloride, hydrochloric acid, HCl. We worked with this, didn't we? So hydrochloric acid is a hydrogen atom and a chlorine atom. They share a pair of electrons. Chlorine is more electronegative than hydrogen, so the chlorine is negatively charged and the hydrogen is positively charged. The electrons will spend more time around the negatively charged atom they will around the hydrogen. So they're unevenly charged. So it's like 2 parents sharing custody of a child. But these 2 parents, one lives in California and the child stays with them all year long except for 2 weeks when they fly over to New York and the other parent gets them for 2 weeks. That's uneven sharing. The child does belong to both parents, but the both parents are responsible for that child. Maybe that's a better way of saying it. But that child spends more time with one parent than the other. That is polar bonding, right? This is polar bonding, not nonpolar, polar. Uneven sharing. This is an example dipole moment. A dipole moment is a measurement of the charge separation between the 2 atoms. Has a vector quality, which I don't believe many of you know what vector means. So that just means it has both size and direction. So this thing has size and direction. It says it right here, direction and magnitude. Magnitude means size, right? How big something is. When there's a larger difference between electronegativities between the atoms, the dipole moment becomes larger, right? And dipole just means there's 2 poles, right? Dipole is just a measurement of the separation between charges. How big a difference do you have? That's all dipole means. So let's take a look at hydrochloric acid. This is a polar bond. This is this symbol here is the lowercase delta, and it's a Greek letter. This is not an S, but it looks like an S with a little funky curve to it. And this is called delta. That's lowercase delta. This is positively charged partial. This actually means partial, right? So this is a partial charge. So this is a partial positive charge. Partial positive charge. And this is a partial negative charge. Well, why is it partial though? How can you have it partial? Well, what happens is when that electron that they're sharing, these 2 electrons they're sharing, They're sharing these two electrons here. When this electron ends up over here with chlorine, this becomes negative, but then it jumps back over with hydrogen, and the hydrogen becomes neutral. When it's over here with chlorine, chlorine is negative, but hydrogen is positive. But when it's back over here with hydrogen, hydrogen is neutral, but so is chlorine. So it's only partially, part of the time with hydrogen and part of the time with chlorine. So it's part of the time negative, part of the time positive, and so you get this partial negative and partial positive charge. How big a difference? It's a partial +1 and partial -1. So chlorine's an electron, hydrogen's an electron. So this is hydrogen's electron, that's chlorine's electron. So they're sharing this pair, all right? So now let's take a look at this and see which one of these two have polar covalent bonds. Now, in order to really figure this out, to sit down and figure it out, I have to give you a chart that has electronegativities. Nobody expects you to memorize these. But, you know, it's important that you understand this concept, right? All right, so when we look at lithium-2 oxide, right, lithium oxide, I'm going to go ahead and show you how you would actually calculate the differences between these and see if you can see how easy it is to do. But I'm not going to have you do this on the test, nor do I expect you to be able to need to calculate it. But I do need you to understand this idea of polar covalent bonds. It's a really important concept in biology. This polarity is going to make a big difference when we're trying to make a cell and we start talking about membranes, okay? So let's take a look and see how you read this. And when you have an electronegativity difference of 0.4 or less, then we call this nonpolar. So when the difference between these two, this atom and this atom, is 0.4 or less, then we call that nonpolar. If it's greater than 0.4 but less than 0.7, we call that polar. So you have that partial positive and partial negative. If the difference is larger than 1.7, then we call it ionic, because now the difference is so large they don't share partial custody of those electrons. One takes it and the other one gives it. All right. So this is ionic. All right, so let's take a look at the difference. You know, if we did the drawing and we looked at oxygen, we'd know that oxygen is bonded to lithium, and it's bonded to lithium. All right, not quite that extreme a bend, but whatever. The two lithiums come in, and what's the difference between lithium and oxygen? Oxygen's 3.5, lithium's 1. What's the difference? The difference is 3.5 minus 1 is, I hope you say 2.5. What's 2.5? It's ionic. So, you know, an easy way of doing this, an easy way of remembering this, is that if and this, I said it before, if your elements are in this row, in this column rather, and your other element, this bond, is in this column, then you know it's going to be ionic, because and the reason behind that, by the way, the reason behind that is that this is so electronegative compared to this. If you do the subtraction, 3.5 minus 1, of course, hydrogen's an exception, right? If you do hydrogen and oxygen, you separate the two, 3.5 minus 2.1. I hope everyone says it's what? 1.4, right? 1.4 is less than 1.7, more than 0.4, so it's actually very polar, but it's not ionic. So hydrogen is an exception. So anything here in this column, if you look also in your periodic table, you'll notice hydrogen is not really in group 1. It's set aside. All right, in this periodic table, it's here. Also explains why there's no noble gases, because noble gases don't have, we're not dealing with electronegativity with noble gases because they have a full octet. All right, so in this chart here, we have oxygen with 3.5, lithium with 1.0. So, but if you look at all these differences, oxygen with any of these is going to be higher than 1.7. So oxygen with any of these is going to be ionic. 3.5 minus 1.5 is 2, still bigger. So again, oxygen with any of these is going to be ionic. Fluorine, any of these with lithium or any of these with beryllium is going to be I'm sorry, with fluorine with any of these with anything in the second column is again going to be higher than 1.7, so they're going to be ionic. So these two columns and these two columns always form this ionic compound. This is the reason why these are stronger, have a stronger pull on the electrons. So when we take a look at this, we can see that lithium is ionic. Sodium chloride, sodium 0.9, chloride 3 minus 0.9, 2.1, much bigger than 1.7, ionic. Or you can just remember anything in these two columns combined with anything in this column or this column except for hydrogen, everything in those columns with these two columns, they're going to be ionic. Sodium, again, sodium and fluorine. Those two columns again, ionic. So realistically, this should have been easy to know that all three of these are ionic. I said it in class many times, but here is the reason why I decided to go ahead and show you. Now, let's go ahead and take a look at this nitrate. We had that in class 2, didn't we? Go ahead and take a look at nitrate. You have a nitrogen, and nitrogen is 3.0, and oxygen is 3.5. The difference between nitrogen and oxygen is, right? The difference between nitrogen and oxygen is 0.5. 0.5 is bigger than 0.4, isn't it? So 0.5 is actually about here, right, somewhere around there. So what is it? It's polar. These are polar bonds. So there's 3 of them, 1, 2, and 3. And there's 3 oxygens. And it's really a complicated structure. I wish they would not have even discussed nitrate, except that they did. So I'll go ahead and draw it. As it turns out, there's all kinds of complications with why. These are some exceptions to the rules. It's something we call resonance, and the electrons jump from one atom to another, try to balance everything out, and the thing turns out to be an ion. The whole molecule turns out to be an ion. But that's a whole nother story that has levels of chemistry in it that we're not going to get into. But the key is that you understand that this thing is ionic here, this thing's ionic, this thing's ionic, and this is the only one that's polar covalent, because this bond here and this bond here and this bond here, they're all polar covalent because nitrogen and oxygen are so close to one another, not quite the same, right? Bigger than 0.4, so it is in fact a polar covalent bond. All right, let's go on to the next question. So covalent bonds usually involve carbon, oxygen, right? Nitrogen, hydrogen, which are all essential to living things. Covalent bonds are all going to be in about 96% of the atoms in your bodies are composed of just these: oxygen, nitrogen, hydrogen, and carbon. I told you guys, right? I said these elements, these 9 elements, are the ones that we have to concern ourselves with in the body, and I numbered them. And if you go back and look at that in your notes or in the videos, you'll see that these are the top 4 that we talked about. Just these 4 elements, as I said, as is written here, 96% of the atoms in your body are these 4 elements. All right, glucose, fructose are all forms of chemical energy that are made of carbon and oxygen and hydrogen. Also, all covalent bonds. So our bonds between carbon and hydrogen atoms, something like methane, nonpolar bonds. All right. So now, what do you guys think? What do you think between carbon and hydrogen? Is it polar or nonpolar? Now, if you looked at just the periodic table, you might be saying to yourself, well, it's probably ionic because hydrogen's on this side and oxygen and carbon's on this side. But if you take a look at the difference between them, you actually look at this chart, which you didn't have, so you couldn't have. 2.5 minus 2.1 is a difference of what? Of 0.4. So this is kind of one of those things that is it polar, is it nonpolar? Well, it's zero point 0.4, and so really polarity is a spectrum. So you can say it's the weakest possible polar, or is it the strongest? It's the weakest possible nonpolar, or is it the least non polar? You know, look at it any way you want, but we're just going to go ahead and call them, right, nonpolar. And that's what, because it's 0.5. It's not greater than 0.5. The difference is not greater than 0.5. And so, okay, so this is, so far we've been talking about what these molecules that we call intramolecular, right? So they're the kinds of bonds that hold atoms together. They're the kinds of bonds that make a molecule. All right, so now let's talk about hydrogen bonding, which is probably one of the major sources of functionality that we have in our body, and that's what happens when these polar bonded molecules get near each other. So water is the perfect example. This is one of the reasons water is so special. In fact, it's the reason water is so special. So we have this tiny little thing. Hydrogen bonding, by the way, you can think of it as like is almost the ubiquitous answer. It's the answer to so many biological questions. Okay, so here you have oxygen has a partial negative charge. Here's hydrogen with a partial positive on each, right? And each water molecule is floating around. And you saw me draw this in the first movie that I made for you with your lab, from your lab. And what's going to happen between a partial negative and a partial positive? I hope you remember that opposites attract. So they're going to pull on each other. They're not. Now, is this holding a molecule together? No. This is one molecule of water. This is another molecule of water. And so this water molecule and this water molecule attract one another, hydrogen to oxygen. We call this type of bond, it's a bond in a sense. It's not really a bond between atoms, right? It's a bond or an attraction. It would probably be better said hydrogen attraction. This hydrogen bond is a weak attraction. It's relatively weak between two water molecules, or between any hydrogen bonded to any atom like oxygen. There's going to be this partial positive and negative charge. Now, if we went ahead and did the electronegativity again, looked at the electronegativity of oxygen and hydrogen, you see 3.5 minus 2.1, and that's 1.4. And so we know it's less than 1.7, which is what would make it ionic, but it's greater than 0.4. So this is a polar bond. So these are polar bonds here. And in fact, they're the classic example of polar bond. When you hear polar bond, you should think water, because this is exactly what almost the definition of a polar bond. Oxygen and hydrogen pulling on each other unevenly, creating a partial negative charge over here, creating a partial positive charge over here. So this weak attraction between the molecules kind of keeps them together. That explains how a water spider can walk on water. And the reason water spiders can walk on water is because this surface tension, which is caused by the water molecules pulling on each other. Another example of surface tension, if you drop one drop of water on a penny, one drop at a time, very carefully, the water wouldn't overrun. What would happen is, if you had this penny, right? Yeah, this penny looks more like a bottle cap or whatever. You drop this water on it, one drop at a time. What would happen is that instead of the water going over the sides and dripping off initially, what you'd get is a bulge. The water would just keep dropping on top of the penny, and you get almost a lens happening on the penny. You could try this at home if you want. So instead of the water running off, the water sticks to itself. Water is sticky. This is the sticky part. This is the glue that holds it together, this hydrogen bond. You don't believe water's sticky? Why doesn't the water fall right off of you when you get out of the shower? Why do you need to get a towel and dry yourself off? Because that water is sticking to your body. It's sticking to you using hydrogen bonds. All right, so let's take a look at this. Which hydrogen atom donates an electron to another atom? So which of the following is true about hydrogen bonds? A hydrogen atom donates an electron to another atom. That's not true, right? We're not talking about bonds. With hydrogen bonds, we're not talking about bonds between atoms. They're attractions between molecules. So that is absolutely a false answer. All right, a hydrogen atom attached to an electronegative atom in a molecule, highly electronegative atom in a molecule, is attracted to an electronegative atom in the adjacent molecule. All right. So hydrogen attracted to an oxygen, for instance, is attracted to the oxygen in the other molecule. So the partial positive of the hydrogen is attracted to the partial negative of the oxygen across from it. So if we take a look at this, and this is hydrogen, this is a partial positive charge. Here's another hydrogen with a partial positive charge. Here's a hydrogen with a partial positive charge. Why is a hydrogen going to, and this of course has a partial negative charge. Why are these hydrogens facing the oxygen? They're facing the oxygen because the oxygen has a partial negative charge. The oxygens repel each other, the hydrogens attract one another. Now this is very important because this is going to explain why ice floats. This is going to explain why, and think about it. What do solids do in liquids usually? If in their own liquids, if you take liquid iron, a hot piece of iron, you take a large piece of iron, you drop it in a pool of hot iron. Before it melts, it's going to sink to the bottom. But this ice floats on water. It's extremely important. If it does that, in part because of what you're seeing here, this arrangement of the molecules. They arrange each other because the negatives repel and the hydrogen is attracted to the oxygen using these hydrogen bonds, right? These are hydrogen bonds. And so yes, B is wrong. B is the answer. Hydrogen bond creates a covalent bond with another atom. Absolutely not, right? We're not talking about covalent bonds. We're not talking about bonds that hold molecules together. We're talking about bonds between molecules. So a hydrogen atom inherits an electron from another atom. I don't even know where that comes from. All right. So obviously the answer is B. Great. So an example of how hydrogen bonds are significant in living organisms is that they are vital to components of DNA. In fact, the reason DNA has its shape is the reason it has that double helix character, shape that we all recognize, is because that some of you actually are wearing on your shirts, is because hydrogen bonds pull the hydrogen from one atom or from one part of the molecule is pulled by the oxygen or nitrogen on another part of the atom, and you have these hydrogen bonds occurring throughout the molecule, and it twists predictably into this double helix. All right. Okay, so let's go ahead and try to do some review. Can you tell me which of the following contains a nonpolar covalent bond? All right. Look at it. Think. The answer should be real easy. And by the way, this is the only question, the kind of question I'm going to give you when it comes to this. I'm not going to have you calculate electronegativities. All right, I hope you said that this is fluorine. This is the one nonpolar covalent bond. How did I know that without calculating any numbers? Fluorine is bonded to itself. If an element is bonded to itself, they both have the same electronegativity. Their difference is 0. Its electronegativity minus its own electronegativity is 0. So this is always less than 0.4. This is always nonpolar. Hydrogen chloride, it was an example of a polar bond. Lithium and fluoride. Lithium and fluoride. Look at this gray. What happened here? Fluoride should have 7. Why does it have 8? Lithium should have 3. Why does it have 2? Because fluoride took lithium's third electron and lithium gave it. And one of the things that we would want to draw if we were doing this and didn't want to get points taken away is add a -1 here and of course a +1 here. Because this is a what? An ionic bond. So this is ionic. This is nonpolar. All right. So here between hydrogen and chlorine, we know it's a polar bond. We discussed it earlier. So this is polar. And you could do the numbers if you like, but it is polar. And the one molecule that I could put on the test on Friday, I can almost guarantee you it's going to be on the test, is water, H2O, H2, and O. And that is always going to be polar. It is the example of a polar molecule because the different electronegativity difference between hydrogen and oxygen leaves you with a polar bond. This is partially negative. This is partially positive. Remember, this is the Greek letter delta. Partially positive. And this is what leads you to having hydrogen bonds. At least one of the examples. Other molecules can also do hydrogen bonding. Anytime hydrogen is bonded to a strongly electronegative atom, you're going to have this polar bond, and that's going to allow hydrogen to attract other partially negative molecules. All right, so that's it for these four. Let's go on to the next one. What about this? Which of the following occurs in a hydrogen bond? All right. So which of the following is going to occur in a hydrogen bond? Should be able to answer this. Let's try it. A hydrogen atom shares an electron equally with another atom. Well, wow, there's so many things wrong with that. First, if it's a sharing electrons covalent, right? Hydrogen bonds happen between molecules, not between atoms. Sharing of electrons happens between atoms in a molecule. And secondly, electron sharing equally is nonpolar. And hydrogen bonds are the result of polar bonds. So on various levels, that's wrong. One atom gives another atom an electron. Well, we call that, so this is nonpolar, right? Can you guys please pay attention to how I'm going through these practice questions? I'm not just trying to find the right answer. I'm asking myself, how are these wrong ones wrong? So if I'm asked a question on a test in the future and they give me another question with similar answer choices, I'm more likely to be able to answer that correctly. So one atom gives another atom an electron. We call that what? Ionic. Certainly, and again, both of these are dealing between atoms. Hydrogen bonds happen between molecules, right? C, two positively charged atoms attract. Well, that's, again, first we're talking about atoms, and this is occurring between molecules. So let me write that in. Between molecules. And the second thing is two positively charged atoms attract. What? No. A hydrogen atom bonded to an electronegative atom in one molecule is attracted to an electronegative atom in another molecule. That's the answer. Two different molecules, you see, molecule 1 and molecule 2, between molecules, not between atoms. And the highly electronegative, the hydrogen bonded to one highly electronegative atom is attracted to the electronegative atom in another molecule, or another part of the molecule in the case of DNA. So, okay, so that's D. All right, what happens to the electrons in an ionic bond? Ionic now we're talking about. Valence electrons from one atom is donated to another atom. Well, that sounds right. I'm going to go ahead and put a question mark on it because I think that's right. But have I chosen A? Did I just choose A and just move on to the next question? No, because I need to make sure I'm not making a mistake. This is the kind of thinking you have to have when you're doing multiple choice questions. You have to ask yourself, is there a better answer? Electrons are shared equally between two or more atoms. That's what? What do we call that when that happens? Hopefully you say covalent. So this is not ionic, right? Electrons are shared unequally between two or more atoms. What do we call that? Oh, by the way, This is called nonpolar. Covalent. Of course, C is polar. Covalent. So it's not C. An atom in one molecule is attracted to a more electronegative atom in another molecule. What do we call that? One molecule to another molecule, we call that hydrogen bonding. All right, so it's not that. So which one's an ionic bond? I'm convinced it's A, because I knew what the others were. Let's go to the next one. Which type of bond occurs within this molecule? This is between nitrogen and hydrogen. All right, so what's happening here? Hopefully you're telling me that what's happening here is that each one of these is a polar covalent bond. Right? There's 3 bonds, yes, but it's complicated. If you try to do the list dot structures, it wouldn't work out as simply as the ones we've been discussing. But in any case, nitrate has definitely a polar covalent bond between each of the nitrogens and a hydrogen. So are they hydrogen bonds? No. Why not? Because hydrogen bonds happen between molecules. So let's make sure we understand that. Is it an ionic bond? No, because this is polar covalent. They're sharing unevenly, but they're sharing. So it's not an ionic bond. And you could do the math, or you could ask yourself, are these metals combined with a nonmetal? The answer to both of those answers would be no, so they're definitely not ionic. Nonpolar covalent bonds, remember the ones I'm going to look for with nonpolar, it's going to be like nitrogen bonded to nitrogen, right? For sure, you're going to have, in this case, a nonpolar bond. Oxygen bonded to oxygen, right? Hydrogen bonded to hydrogen. All these are nonpolar. These are the kinds that you're going to see on the test, just so you know. So nonpolar covalent bonds, it's not nonpolar. And of course, the answer is polar. So I'm satisfied with that. How many valence electrons are present on this atom? Well, hopefully by this time you know that we're talking about 1, 2, 3, 4, 5, 6, the outer shell, 6. Looked at your periodic table, you would see that this is sulfur, and sulfur has 6 electrons in the outer shell. So you should just be able to count 6, first of all. And secondly, to verify, to think about it, sulfur is in the 6th group, so it has 6 electrons in the outer shell. It's just that easy. So the answer is 6. Let me keep the color coordination the same. Answer 6. It's not 10 in the outer shell. Valence means outer. It's not 16 in the outer shell. It's not 14. It's 6. 1, 2, 3, 4, 5, 6. Outer shell. All right, next. You've done well so far. Let's fill in the table and review everything we've learned. All right, so let's do that. Type of bond, the bond that occurs between carbon and oxygen atoms to form carbon monoxide. Carbon and oxygen, right? Carbon and oxygen. So what kind of bond is that? It's a covalent. So that takes us to the end of the video. You can delete that last page. For sure, you need to know that what an ionic bond is, what a polar covalent bond is. You should know these 3 examples. You should know what a nonpolar bond is. You should know at least 1 example of 2 atoms that are bonded, the same element bonded to each other. Hydrogen, the perfect example, because it only has 1 bond. And hydrogen bonding, you should know what it is. And of course, the perfect example again is going to be water, hydrogen bonding to water, and lining up with a partial negative, partial positive, and partial positive, partial positive, and partial negative. So you should have that lining up, and it'll continue to line up as you see. They'll line up and face each other based on the positives and the negatives, and they're attracting each other, and the negatives repelling each other. All right, that's it, guys. Have a good one. Study hard. You probably won't watch this till tomorrow, but whenever you do watch it, review it, and I hope it helps. Goodbye.